Welcome to the lecture on solidification of pure metals and alloys. So, in the last class we had discussed about the concept of solidification, the principles behind solidification, why solidification occurs, how it occurs, how it progresses. So, through the mechanism of nucleation and growth, as we know that there will be birth of tiny grains, tiny nucleus and then that becomes stable under certain conditions of temperature, thermal conditions, and further depending upon further conditions of growth, the nuclei further get added, atoms are getting added to the first atom, and then this is how you get the grains. So, since you have the domain and you have the nucleation at many points, so anyway at every point you have the nucleation of new grain, and then that grain develops to its size, and then from other sides also the grains are coming. So, anyway they are basically approaching each other, and then they will have one common surface, that is the grain boundary. So, this is how the grains are formed. So, you can refer to the books of phase transformation of materials. There are many standard books which talks in deep about this nucleation and growth concept, that how nucleation, what is the rate of nucleation, how the rate of growth varies, what are the concepts. So, that you can study. Let us discuss about its use and how we can further interpret it for the solidification of pure metals and alloys. So, as we discussed that in the case of pure metals, so pure metals, whenever we have purity, whenever the metal is pure, pure means most of the pure metals they will freeze at a common temperature, at a fixed temperature. So, that is how we define pure metals, and if they are not solidifying at a fixed temperature, then they are the example of alloys. Now, in the case of pure metals, what happens that when the temperature at any point will basically come to the equilibrium temperature, when we are pouring, basically the temperature is higher than the solidification temperature or the temperature at which it freezes. So, once it reaches there, in that case with slight undercooling, there will be solidification, and then there will be latent heat release. So, once you have latent heat release, then that will basically be transferred to both the sides, and this is how since it is transferring the heat to another side. So, as we see that once you have the liquid in this liquid touching this boundary, and here everywhere is liquid, basically all is liquid. So, once it touches this boundary, and in that case if there is heterogeneous nucleation condition, and it is practically that whenever we cast any material. So, in that case if this is the mold wall, it is at lower temperature and it has many sites where the nucleation starts. So, if the nucleation starts here and largest undercooling is felt here, so you will have that we had discussed that you have initial solidification happening here. And since, because as we know that when we if you look at the cooling curve of pure metals, so once you have reached this temperature and there is slight decrease in temperature from this position, then there will be formation of tiny grains, and that is nucleus, and then these nucleus. So, once they are transferring the heat, they are transferring the heat in this direction as well as in this direction. So, this side is the sand or air. So, this is your sand, or you can have air or so, whatever it is. Now, so heat will be transferred to this direction as well as in this direction. So, that heat is nothing but the latent heat. superheat has already been released up to this point. So, this is the degree of superheat and this is already released up to this point. Now, once you come here, then in that case the latent heat which is released, now this latent heat once it goes to this direction, the immediate liquid which is there, its undercooling is reduced. So, anyway because of these conditions there will be undercooling going on, there will be basically drop of temperature going on. Now, in that case what happens? So, suppose nucleation will start in the whole domain, if whole domain's temperature is coming near to the equilibrium temperature, but that does not become the case. Basically wherever there is largest undercooling, certainly the temperature will fall more rapidly at this place and the time will come first only at that place where the temperature comes equal to the equilibrium temperature. So, this is your melting temperature or equilibrium temperature. Now, what we discussed that from here once the heat goes into this direction, whatever undercooling this region might have experienced, this undercooling basically is reduced. Suppose this temperature is suppose 800 degrees centigrade at which the solidification has to start. Now, let us say for copper it is 1083 degrees centigrade. So, suppose at 1083 degrees centigrade the nucleation has started. So, what happens in this zone also, here the probable temperature will be close to 1085 or maybe 1084, 1086 or so, which will basically come towards 1083, so that it will also start solidifying. Now, the thing is that when heat releases in that direction, then its temperature becomes more. So, that undercooling which it could have experienced, that is reduced. So, nucleation is not promoted here. So, once you have nucleation here, so certainly up to certain distance you can experience that because of degree of, depending on the degree of undercooling or depending upon the rate of heat extraction, you can see that there will be some formation of these small tiny grains which are spherical or which have no directionality, they are known as acquiesced grains. Now, what happens that the heat flow is primarily going in this direction. So, and since the undercooling experienced or the temperature drop here, that basically is delayed. So, and here in this case that since it is less and at so it will be closer to the equilibrium temperature, in that case what happens, the nucleation does not remain predominant. So, in the early stages of the solidification, the nucleation is predominant, but as the time progresses, because of the heat release and because of the equalization of the temperature in the remaining area, what happens that the nucleation does not remain predominant, and in fact in that temperature region the growth becomes predominant. We had seen earlier by looking at, so rate of nucleation and rate of growth was going like this. So, what we saw that if your rate of, so rate of growth will be maximum towards this. So, in that case in the larger, so if this is the equilibrium temperature, so rate growth basically is predominant when the temperature is a little higher, closer to the equilibrium temperature. So, that is why then what happens, the growth starts. So, the growth of the grain starts. Now, the nucleation ceases and the growth of these grains start. Now, growth of grain basically will normally take place in all the directions depending upon the so, basically you have growth going on in all the directions because heat transfer may take place in every direction, but then because this being the primary direction of heat extraction. So, primary growth is taking place in this direction. So, this way this growth which takes place here, these are the kind of grains, they are known as columnar grains. So, this grain is, so initial grains are Acquiesced grains, and these grains are known as columnar grains. This is the typical structure of pure metals, and this growth continues till this growth itself, this continues till the center line of the casting. So, from this side also you will have similarly you will have the fine Acquiesced grains initially, and then so after that you will have the columnar grains extending till the center of the casting. Like that you will have the structure, microstructure in the case of pure metals. So, pure metals show like this. So, what we see in our slide, that you have in early stages of solidification, the nucleation will be predominant, and the first solidified cell production that results into release of latent heat of fusion, and remaining liquid rapidly loses the superheat. So, that is what we see here, and that since it loses its superheat, so the chances of further nucleation stops and the chances of growth predominates over nucleation, and that is how the solidification takes place. So, what happens if you look at the temperature at any point, if you when you pour the liquid metal in this, at that time the temperature is, suppose you are giving the temperature like this, then what happens that as you see that whenever you start pouring the liquid metal into it, the immediate solidification starts at basically the mold walls. And so, if this will be the distance from mold face, so at 0 time you have this temperature, suppose. Now, so at that time distance from, so everywhere you have at the mold face, and you go suppose in the mold center, maybe this is the mold center, suppose this line is the mold center. So, what we see is initially your temperature is everywhere the same, but then quickly as the time progresses, here the temperature comes down. So, this way you will have the temperature line. Slowly after some time again, maybe that you have your growth goes like this. So, suppose this is your equilibrium temperature. So, this is the equilibrium temperature. In that case what we see is that at this mold phase what you see is slowly. So, this way that at the center you have temperature, at the mold phase the temperature is becoming quite less. So, the solidification has started here itself. At this time itself, at the phase the solidification has started, whereas here in this case that is not the case. Here already it is solidified, and at this point the temperature. So, here at this point the solidification will start. So, this way as the time progresses you see that there will be temperature more in the central region, you will have more temperature in the central region. So, suppose you have a casting, suppose you have a casting here. In that case, if this is the central region, then in that case once you pour, suppose this is a casting and this is your sand, so once you pour the liquid metal into it, then what will happen? The first solidification will start at these places. Then after that you will have start forming the columnar grains. And so this is how what we have understood is that your initial formation will be of the aqueous grains, and then further. Now if you look at this temperature, the temperature drop will be quite fast at this point. So if you take this point as 1, this point as 2 and this point as 3, what we see is that normally the temperature drop, if you look at the cooling curves, now at the first point it will quickly down, it will be quickly down. So it will come and then it will go like this. And similar, suppose this is the equilibrium temperature, second point will come and then it will go like this, third will come and then they may go like that. So this way you have the delay, these regions, this is the second point and this is the third point. So this way you have you see that the temperature in this region is more and more, it is solidifying in the end. So what we see now, this kind of solidification mechanism where you will have initially the formation of certain small thickness, and then this thickness further grows slowly, and this grows in a very uniform way. From both the sides the growth of these cells goes on continuously, and this growth continues till these grains meet at the center. So in this way the solidification will cease at this point, because from both the sides the solidified cell are approaching each other and they are meeting there. So this way your solidification is complete here. So what happens that with time, suppose you have, this is the section which is to be solidified, what you see is initially all is liquid, and with time what will happen that your some portion will get solidified. So this will be solidified at certain time. So if T is 0, it will be T1, T1 is more than 0. Similarly, after some time further you will have this much solidified. So this will be T equal to T2. So here there was at 0 time there is no solidified cell, there is some thickness of the cell, that is D1. So and then after at time T2 the solidified cell is thickness is D2. So T2 is more than T1. So this way what happens that as the time progresses, the thickness of the solidified cell goes on increasing, and it is increasing in a plane way. So the front is moving in a plane from both the sides, the plane that the front is moving in a planar way, in a straight line way, as you see here, that they are moving on the inner sides, and it will go till it reaches in the central portion. So at certain time it will completely solidify. So this is an example of plane front solidification. So what we see is that this is a case of plane front solidification, and the thickness of skin solidified, this is known as the skin. So the skin which is formed, initially you will have a very thin skin formed, and slowly the thickness is basically increasing. So the thickness of this skin solidified, that will be basically depending upon the time, and the formula d equal to k root T minus C. This formula tells that what will be the thickness of the cell formed at certain time. So, K and C are constant and D is the thickness of the skin. So, the K and C, its magnitude, they are determined by the size of casting and how fast you are extracting the heat from the mold. So, that will be depending upon the type of the size of the casting, then type of the mold, what kind of mold material is there. So, based on that, the constant K will be depending upon, and this C is largely determined by the degree of superheat. So, this way you can find the value of the thickness, thickness of the solidified cell. Further, if you do the analysis of the solidification time for a casting, then it has been found, you can study it, and it is seen that the solidification time basically is proportional to the square of the ratio of volume to surface area of the casting. So, that rule is known as the Suvorov Rule. Suvorov Rule. So, this is proportional to V by A square. So, in this case, this is known as Suvorov Rule. So, this is something about the solidification of pure metals, where the metal is expected that it is freezing at a constant temperature, or even it may be applied in the case of eutectic materials, eutectic composition, where the freezing is carried out at a constant temperature. Now, we should discuss about what is the mechanism of solidification in case of alloys. So, as we know that in case of alloys you have a freezing range. So, once you see the phase diagram of any binary alloy, you will have the phase diagram like this. So, what you see, this is the solute percentage. So, what happens, when the temperature drops, the solute particle, so any solid which is precipitating out, this solid will have the, so at any point you have solid as well as liquid. Now, what we see is that at this point you will have the solid as well as the liquid. This is the concentration of the precipitating solid. So, at this point A and this point is B. A is the point which talks about the concentration of the solid, solute in the solid, whereas in the B part the concentration of the solute is different, that is more. So, the liquid which is there in the adjacent region, at the same time you will have solid as well as liquid. The solid is having lower solute concentration, and the liquid which is adjacent to it, it has the higher solute concentration. Now, as you see that since with the increase in concentration of the solute percentage, the liquidus line is basically what we see is, this is liquidus line and this is the solidus line. So, with the increase of the solute concentration, the liquidus line is basically going down, the liquidus temperature line will be less. Now, what happens because of that? Now, what we see is that if you talk about this instant, you will have solid of this solute concentration, and so this, suppose you take XA and XB, solid of XA solute concentration, liquid of XB solute concentration. Now, this sets up a concentration gradient. Now, because of this concentration gradient at this interface, if you take this point, so if you have, this is the solute concentration in the solid. Now, at this point you will have this way your concentration will vary. This is the concentration on this side. So, this at this point at the interface, what you see that there is large. So, at this point you have, this is the concentration of solute in the solid, and this is the concentration at the interface of the solute in the liquid. So, what happens, because of this very high value of solute concentration in the adjacent liquid, if your already you have this much of solidified layer and it has to move further, in that case what happens, since the solute concentration here is quite high, the liquidus line or liquidus temperature will be quite low. So, this liquidus temperature will have a gradient, it go like this. This is the equilibrium temperature. So, this may be the equilibrium temperature. So, basically because of this solute concentration difference, there will be another new this liquidus temperature line which is defined, liquidus temperature line. This liquidus temperature line is because this is earlier liquidus temperature line which has gone modified in this shape, and because of that what happens, what you see is that in this region that this temperature is quite. So, here the liquidus temperature line has come down quite considerably. So, this is, so because now this is basically, now let us see how the solidification will proceed in that case. Now, if your cooling conditions are so that you have the temperature gradient line 1, if you have 1 as the temperature gradient line, if your temperature gradient goes like this, because this is your solidified, you have the distance from the mold wall and this is basically the temperature. Now, in that case what happens, if this is, so if you have this is as the temperature gradient line, and if it does not, it goes past this liquidus, this gradient line, this concentration gradient line, in that case you will have a plane front solidification. So, what you see is that the temperature is near the liquidus at this solid cell, and that is why slowly the temperature will, slowly the temperature will come down and the nucleation will start and there will be plane front solidification. Now, this is a very high kind of heat extraction rate. So, normally that is not achieved. So, what happens, your practically you suppose get this number 2. If 2 is the temperature gradient line, what you see that in the case of 2 you will have this region which has the temperature lower than the liquidus temperature, and this zone is said to be undercooled zone. And this zone has become undercooled because of the change in the solute concentration. So, that is why, and that is why this phenomena is known as constitutional supercooling or undercooling. So, since this undercooling is experienced because of the change in the concentration, so that is why constituents percentage or so, or concentration of the solute. So, that is why this is known as the constitutional undercooling, and this is prevalent whenever we talk about the solidification of alloys. Now, if we see that if the solidification, I mean temperature gradient line goes like this, even 3. So, basically here it becomes even large enough. In this case, this is the degree of undercooling that it experiences. So, in fact, in that case the temperature differential is low enough to promote the random nucleation. Now, what happens because of this, how the structure develops? So, in the case of alloys, what happens? Now, in the case of alloys, as we see that whenever the liquid metal will be poured, then the first, certainly because there is a large undercooling here, so you can have this very small acquiesced grains here, but the thing is that slowly, now in that case you develop. Now, in this case what happens, because of this undercooling, what we see is that in the zone somewhere you have the formation of a spike, and also there will be growth even in lateral directions. So, what happens from that solidified cell itself, in the near zone, in the liquid zone itself, you will have the formation of such a spikes type of structure or arm type of structure, tree like structure. So, this type of structure which is formed, they are known as dendritic structure. So, this is all happening because of this undercooled zone. So, in this case you will have many places, you will have these kind of spikes or tree like structure or so. So, this way it goes. So, you will have, this is known as, and you will have the growth columnar grains, but then you will have the formation of these spikes or dendrites. So, that is known as columnar dendritic structure. Now, what happens in the middle zone? In the middle zone what happens? Now, in the middle zone where it becomes the undercooling is, because the cooling rate becomes even slow, as we know that as we go towards the center portion the cooling rate becomes even slow. So, this differential becomes even more. So, that is why here you get again the acquiesced type of structure. So, this will be acquiesced dendritic, and this is columnar dendritic. So, what happens, you will have, so if you have the wall here, you will have the this kind of, so this is a primary dendrite and these are the secondary arms. What happens, the situation, this is very much deleterious, because when you have such dendrites, suppose you have another dendrite whose arm has gone like this or so. Now, what happens if the liquid is entrapped in between these arms, then this liquid is basically the source of shrinkage defect, because there is no plane front solidification. It is a case of the tree like structure formation, and in between the arms there may be trapment of liquid steel or liquid material, and that may be the source of some defect. So, that is a case of dendritic type of solidification. So, what we see here is that when there is freezing range of solidification, precipitating solid differs in composition from liquid, and then concentration gradient is set up, and depending upon that you may have plane front solidification. When you have this condition, you will have undercooling ahead of the advancing front, and that will be constitutional supercooling, and then that promotes the promotion of growth of spikes extending into the liquid, and then there may be the, and in the central zone basically you will have the formation of the equiaxed type of structures, and what you see here is this is how the dendrites move, and then you will have formation of the dendritic structure in case of alloys. Thank you very much.